Okay, let's get started. This is a trend we've been having for a long time. We've been putting many cores on chip. There are good reasons for this. They're simpler and lower power than a single core, and there may be different ways of designing the system, and they enable large-scale parallelism on chip as well. So what we want with more cores on chip is, ideally, we would like to get n times the system performance with n times the cores, right? For some sort of throughput metric, or maybe latency metric. Depends on the application. But what do we get today? So we did an experiment a long time ago now. It was 2006. We took the state-of-the-art dual-core system of the day. This is from, I think, an Intel system. We ran two applications, MATLAB and GCC, one on each core, single-threaded. And we measured the slowdown each application experienced compared to when it ran alone on the same system. So these are applications running together, and they're slowed down when they ran compared to when they run alone on the same system. So MATLAB slowed down by about 7%, whereas GCC slowed down by almost 3x, or a little bit more than 3x. So what we tried to fix this problem, somehow give priority to MATLAB by making it nice in the operating system, by actually nicing GCC, give priority to GCC by making MATLAB nice in the operating system. Nothing changed because operating system schedules two applications on two cores, and you get the same unfair slowdowns. So we call this the memory performance hog, MATLAB. And why does this happen? This actually happens because of uncontrolled interference in the memory system. And in this case, it's the memory controller. Multiple cores share the memory system, and if the algorithms that are employed in the memory system when prioritizing these different applications, different cores, is unfair, you get this sort of behavior. So what happens in this particular case is you run MATLAB on one core and GCC on another core. They both send requests to the memory controller, and the memory controller, for some reason, prioritizes MATLAB over and over until some point. But then it's too late. GCC is slowed down for a long time. And this is only one part of the shared memory system. There are a lot of other shared resources, shared caches, shared interconnects, and potentially shared cores as well. Yes?
Just a question. Is this the same behavior if you
swap the cores?
You run GCC on the first core?
Mm-hmm. Yes.
On the second one?
Yes, you get the same behavior. So it doesn't matter which core you run it on for this particular system. Okay. Basically, the problem is threads requests interfere in the shared memory resources. And this will become a much more bigger problem as we scale the system. There's a lot more points of interference in a system like this. I've shown you this picture a couple of times probably by now. They interconnect the buses, the shared caches, the shared memory, the pins. The problem is, even though threads share the memory system doesn't distinguish between threads requests. Existing memory systems, at least most of them today, people are changing the memory system designs today, but they're mostly free for all. They're shared based on demand. The control algorithms that are employed are thread unaware and thread unfair as a result of that. And aggressive threads, as a result, can deny service to others. Maybe I should lecture from here because it's easier to read for me. This is actually harder to read, right? Is it true? I think it's my eyes, or but basically, okay, it's okay for you. Basically, the memory systems are not designed to reduce or control inter-thread interference. And this was one example that I showed you. And I'll actually generalize this example. It's really easy to write an application like MATLAB. You don't need to be writing MATLAB to induce this behavior. Because the behavior is because of this. I'll abstract MATLAB and GCC as stream versus random, even though GCC is not perfectly random. But if you have a streaming application and a random access application that have equal memory intensity almost, you'll get this sort of behavior very easily in the memory controller. And let's take a look at why. Basically, we did this experiment also after seeing those results. We took an application, very streaming. This is the stream benchmark modified to fit our needs. Basically, what this benchmark does is it initializes two arrays and copies one array to other. There are a lot of other operations too, but we'll look at this. And it copies one array to another in a streaming manner. As a result, it has sequential memory access. As a result, it has very high row buffer locality. Remember the row buffer from the previous lectures? And we measured 96% hit rate for this workload. And it's very memory intensive because we ensure that every memory access is a cache miss in this case. And this is the streaming application. If you want to do the control experiment, we also generate a random application, which does exactly the same thing. but except it does random memory access. And as a result, it has very low row-buffer locality and similarly memory intensive. And if you run these two applications together, let's take a look at what happens. Right. Basically, this is the memory controller. This is the memory request buffer, and let's examine one bank when two applications contend. This is a two-dimensional array of cells, rows, and columns. And let's say blue application is a streaming application. It keeps on accessing row 0 because it has nice row buffer locality. Consecutive addresses are mapped to consecutive locations of the row buffer. And the memory controller, remember, tries to prioritize requests that hit in the row buffer because it takes much shorter. So the memory controller basically keeps prioritizing streaming applications' accesses that hit in the row buffer over the random access applications' addresses that keep missing in the row buffer, because these will take much longer to service. And if the memory controller picks these, the DRAM bandwidth utilization will go down, and the latencies will increase. Per request latency will increase. As a result, if you have a row size of 8 kilobytes and a cache line size of 64 bytes, approximately 128 requests of T0, the streaming access application is serviced before any single access of the random access application. And this could be more as your row size increases, right? So what is the problem? With the DRAM controllers, because a row conflict memory access takes significantly longer than a row hit access, these controllers take advantage of the row buffer. A commonly used scheduling policy for a long time has been prioritize row hit requests first, and everything else being equal, prioritize older requests over others. So it's a little bit better than first come, first serve. There's a priority for the row hit requests. This scheduling policy aims to maximize DRAM throughput. It's a goal. It doesn't perfectly achieve that because there are a lot of other constraints in memory scheduling. But it's a reasonable, simple policy to approximate that. And it's a reasonable policy for a single core system where you have only one thread running. But it becomes unfair when multiple threads share the DRAM system. And we took those stream and random applications that I just described and ran them on, this is Intel Pentium D results, running Windows, Linux, it doesn't matter that much. You take stream and random, you measure the slowdown each of them experiences compared to when it's run alone on the same system. And stream slows down by about 18%. Random slows down by almost 2.8x. And these results were repeatable at that time in 2006 on many different systems. So that's why we wanted to study this problem. And if you run stream with other applications like GCC, you see very similar behavior. Stream is a hog that denies service to pretty much any application that it runs with, except for stream. We did the control experiment with stream, and you see that they have similar slowdowns, as expected, right? And this was Microsoft's, I guess now dead virtual machine, virtual PC. This was the competitor to VMware at that time, so even virtual machines slow down, as expected. So this becomes a greater problem with more cores. This is a result with 4 cores. libquantum, which is very similar to Stream. This is a Spec 2006 application, a quantum computing simulator, which has very streaming behavior, very memory intensive, lots of memory misses. If you run it with these 3 other applications, it slows down very little, but it destroys the performance of other applications that it's running with. The other ones slow down significantly. So you see very unfair slowdowns for some definition of unfairness, or for most definitions of unfairness, probably. Basically, one slows down very little, another slows down by almost 8x. So what are the problems with this? This makes the system vulnerable to denial of service. So you can easily write an application like this and inject it to someone's computer, cloud computer, and you get this sort of behavior. Some other applications slow down significantly. We're unable to enforce priorities or service level agreements as a result of this, because you cannot actually fix this problem in the operating system unless you deschedule some applications, which makes you lose a lot of throughput efficiency. And this also leads to low system performance too, because if you look at this application is the one that's making progress, but the other ones are making very slow progress. If you actually want to maximize for system throughput, it turns out these applications are less memory intensive. Prioritizing those would increase your job throughput a lot more than prioritizing this one, but the memory system is really prioritizing this one. So as a result, what we have is an uncontrollable, unpredictable system. It's unpredictable because the slowdowns depend on which applications you're running with. So if you look here, I believe Omnet is here. Omnet slows down by 8x if it's running with this mix of applications, and slows down by 4.5x if it's running with this mix of applications, because there is no control in the system. Your slowdown, your performance is very dependent on which other application you're running with. in the system. And this becomes an even bigger problem. This is just if you actually have a network on chip, and if you have a lot of unfair policies in your network on chip, we've done some of those studies also, not in a real system, but in simulation. What you could do is you could have some applications potentially, intentionally or unintentionally, accessing some shared resource, memory controller over here, while another application, this is Black-Scholes, that's also accessing or communicating within the network or accessing other memory schedulers, you could see slowdowns that are pretty unreasonable, like latencies, network latencies that are significantly increased because of the unfairness in the system. So how do we solve the problem? Basically, the problem is inter-thread interference is uncontrolled in all memory resources, or mostly uncontrolled. Memory controller interconnect caches. Basically, we need to control it somehow. Or in other words, design an interference-aware or quality of service-aware memory system. I think there are three key challenges, three key questions in designing such a system. First is, how do we reduce this interference, minimize it such that we maximize system performance? This improves system performance and core utilization. And how do we reduce the serialization of requests? And how do we reduce core starvation? And I'll talk about some techniques to do that. How do we control inter-thread interference is a related question, but it's more related to providing mechanisms to enable the system software to enforce different kind of quality of service policies, because we don't want to burn a quality of service policy into the hardware itself. We would like to do that, of course, while providing high system performance. If you would like to control inter-thread interference, it's really easy to do if you don't care about performance, right? You can design a 1,000-core system and run one application on one core, and you get perfect, no interference, and you solve the problem. But that's not an interesting solution. And the third part is, how do we make the memory system configurable, flexible, such that we can actually enable different policies to the system software? Because you don't have a single goal at any given point in time. You don't always want to maximize throughput. You don't always want to maximize fairness. Sometimes applications need performance guarantees. Sometimes they don't, and they run together. So you'd like to have a memory system that satisfies all of those requirements at the same time, which means that the memory system must be configured, because the memory system doesn't know the application's requirements. So I'll hopefully talk about some of these as I talk about two major approaches to designing quality of service aware memory systems. And I see this is my view of what are the two major approaches starting from today's systems and changing them. The first one I call smart resources. Basically, you can have these resources that are designed, caches, interconnect, and memory controllers, that are designed to have this configurable interference reduction and control mechanisms. Basically, change the design of the resources in this case, and maybe hopefully put them together somehow such that you have an overall quality of service aware memory system. And I'll talk a lot about memory controllers today, but we've been looking at interconnects as well. The second approach, which is complementary, is dump resources. Basically, keep the resources as they're today. They're not necessarily dumb today, but they're optimized for something else, right? But keep each resource free for all, such that they do not provide any fairness, but reduce or control interference at the periphery, at the sources, for example. If you think of the memory system as a shared resource, you can do something else without modifying the resource, or while modifying the resource very little. For example, you can throttle injection into the shared memory system such that some applications do not deny service to others. Or you can map the data of applications to different places such that they do not interfere with each other, maybe as much. So this is a different approach. You don't change the resources that much. And I'll show you that actually doing both is probably the best answer, because that gives you different kinds of benefits. So I don't know where we will get today, since we don't have that much time, but ideally we would get to both of them. But today we may spend a lot of time on the memory controller part, and I'd be happy to talk about this other part as well, which we've been working on too. Any questions so far? Am I going too fast? Yes?
Can you go back to the slide where you compare MATLAB?
Sure. GCC? Okay, that's an old slide, far away. Let me skip the animation here. Okay, this one?
Right, okay.
Nope, it's coming.
7%, 3, 4, okay.
Yes.
And then when you generate your ideal screen and random, it's not that it's bad, not that this is worse than ideal random and ideal.
so it seems like this is worse. That's right, because random and well, I wouldn't call them ideal, but random and streaming, they're both very memory intensive. Whereas MATLAB is very memory intensive, but GCC is not. So the impact on GCC becomes worse. So MATLAB doesn't get slowed down that much because GCC is not that memory intensive. Okay. And GCC gets slowed down more because its relative impact, relatively it's running really fast, but it gets slowed down a lot because MATLAB is very memory intensive. That's the reason. So stream and random is very similarly memory intensive, so stream slows down more. And random slowdowns less because it's making slow progress anyway to begin with. But it's still a high slowdown. And that's a very good observation. Why don't they get slowed down similarly to that? Okay. Okay, I'll continue. So let's start with quality of service over memory controller. It's just another exciting topic. Maybe Andre won't agree with me. It's interesting. But this is another exciting topic for me. And we've been looking at this a lot. And I think there's still a lot of interesting things to be done at the memory controller level because it's such an important resource, controlling another important resource. Basically, we're going to look at quality of service over memory scheduling. The job of the memory controller is to arbitrate between the cores and the memory. Basically, it resolves memory contention by scheduling requests. We're going to look at how to schedule requests to provide high system performance, high fairness to applications, and configurable to system software. And we may not be able to go through all the approaches. The key observation, I mean, this is kind of obvious, I think, once you try to provide all of this. The memory controller has to be aware of threads. I do not know of any other way of doing all of this without exposing thread information, like what hardware context generates the request to the memory controller. That has to be there. So I'll give you an evolution of what we have been looking at in this area very quickly, and then I'll jump into some of these interesting, hopefully interesting approaches. So when we first started, when we first observed the problem, we wanted to remember those unfair slowdowns. We want to make them fair. And the first definition of fairness we came up with is, why don't all of the threads slow down equally, right? And the first idea was to have a memory controller that estimates and balances the thread slowdowns. And we're going to talk about this very little. This is not the greatest memory controller, I think, at this point. But the takeaway is that if you balance the thread slowdowns, the threads make kind of proportional thread progress. And this actually improves performance. And for some definition of fairness, it's fair. Basically, you prevent starvation if you can do this perfectly. And this is true especially when threads are similarly memory intensive, so they can make good progress. But this is not the best performing memory scheduler because you don't want to do this if you want to optimize for job throughput, system throughput. Later, we realized that there's another form of interference that happens when you have multiple banks and multiple threads. And parallelism-aware batch scheduling, I'll talk about this in a little bit more detail. The idea here was to rank the threads and service the threads in rank order. The memory controller periodically ranks the threads and services the threads in that rank order. And to prevent starvation, it batches requests. And let me show you the problem we were trying to solve. I'll get back to this very quickly also. Oh, this is much nicer here. Right. Okay, if you look at this, these are two banks in the memory controller, and we have requests from two different threads, the blue thread, thread A, and the red thread, thread B. It may be that these requests arrive in this order. The bank 0 services requests, the blue request first, blue threads request first, and bank 1 services red threads request first. You get a memory service timeline that looks like this, if that's the case. As a result, both threads wait for two requests, right? Two bank access latencies. Whereas if you do this simple change, if you rank one thread over the other, let's say you rank thread A over thread B, and both banks obey that rank order, what happens is both bank 0 and bank 1 service blue threads request first, and then they both service red threads request next. As a result, blue thread completes after one bank access latency, and the red thread completes after two bank access latencies. As a result, thread A waits less compared to a memory controller where you don't do ranking. So you save cycles without actually delaying thread B at all. So that was the principle of parallelism-aware batch scheduling. I'll briefly go over this in more detail. But basically, the first principle is schedule requests from a thread back to back. And somehow by ranking the threads. This preserves each thread's bank parallelism. But this can actually cause starvation, right? If you actually do this, you can cause starvation because the core may be generating more requests. So to prevent that starvation, we have second principle. The idea is batching. The memory controller, and this is a very old idea. People have employed this in disks for a long time, since the 1960s. You group a fixed number of oldest requests from each thread into a batch, and memory controller says, this is my batch. I'm going to service all of these requests here first, and after that, I'm going to prioritize any other request that comes afterwards. That's the idea. This eliminates starvation and provides fairness while you're preserving bank parallelism. Let me briefly demonstrate it pictorially. Basically, you have requests from these 4 different threads that go to these 2 different banks. The memory controller looks at its request queue, and it forms a batch based on some number of requests per thread. And then memory controller ranks the threads somehow. It schedules requests from T1 first in parallel. And other requests arrive in the meantime, and they do not get included in the batch. Otherwise, we would violate starvation freedom. Then memory controller picks thread 0's requests and serves them in parallel. Then memory controller picks thread 3's requests and serves them in parallel. And note that these requests are not serviced because they're outside the batch. They're not oldest in the batch. And then the memory controller picks thread 2's requests and serves them in parallel, and then forms a new batch. So that's the idea of parallelism or batch scheduling. And we'll see the performance impact of it, and hopefully more detail too. OK. So basically, the takeaway is if you preserve within thread bank parallelism, this improves performance, and request batching improves fairness and provides a nice guarantee on starvation freedom. Then we started rethinking memory scheduling in a different way. One thing these previous schedulers did not do well was to prioritize threads that are very compute intensive. If a thread is very compute intensive, if you prioritize that, you can actually improve job throughput significantly because it'll finish its request and it can go back and keep its cores busy. Right? That was the main idea in Atlas memory scheduler. We didn't do it exactly this way, but basically the idea was to prioritize the thread that have attained the least service so far from the memory scheduler. And if a thread is actually compute intensive, it naturally attains the least service for a given amount of time. And it turns out the takeaway for here was to prioritizing these light threads actually improves system performance. So later, we wanted to get the best of both fairness and performance, and that was the idea with thread cluster memory scheduling. Because if you prioritize low-intensity threads, that's good for performance. But if you prioritize all low-intensity threads over the others within this ranking, by ranking them, some threads get denied service significantly. So the idea with thread cluster memory scheduling was to cluster the threads into 2 groups, memory-intensive, or memory-intensive meaning bandwidth-sensitive. That usually tends to be the case, but it's not always the true. And memory non-intensive, latency sensitive. If you think about a compute-intensive thread, it's not memory intensive, but it's very sensitive to memory latency because if you delay that thread by the same amount as you would delay a memory-intensive thread, this thread that's compute-intensive would slow down a lot more because that request is very important for that thread. Whereas if you have a very bandwidth-intensive thread, if you delay one request of that thread, it may not be that important because there may be a lot of parallelism, and it's very bandwidth memory-intensive anyway. It'll stall again. So that was the idea here, prioritizing this latency-sensitive group over the bandwidth-intensive group. And we employed a fairness policy in the bandwidth-sensitive group that I will talk about. So the takeaway here was a heterogeneous scheduling policy that's different based on thread behavior maximizes performance and fairness. OK, later, actually, this is not perfectly memory scheduling. This actually combines this dumb resources approach with memory scheduling. And it turns out this is actually a better approach, I think, overall, if you can do this in the system software. Basically, here the idea was to mitigate the interference between different applications that interfere badly with each other by mapping them to separate channels. So if you have, for example, stream versus random, stream actually destroys the performance of random if they're mapped together on the same channel. But if you map them to different channels, all streaming applications to one channel and all random access applications to another channel, you get much better system performance. Because streaming applications do not destroy each other. Random applications do not destroy each other. And as a result, you don't need to change the memory scheduler also, if all of your application mixes like this.
But when you must know that the application is streaming on when you are located.
That's right. That's the downside of this approach. Basically, if the application changes from streaming and random at a fine granularity, it's very hard to adapt this, right? Yeah. Because you need to do page migration.
And also,
That's right. So what we did was we didn't strictly partition. We basically did a best effort partitioning. Yeah, that's right. If you strictly partition, you can get much worse performance because now you get page faults because of that. But we did best effort partitioning. If I get to it, I'll describe it in more detail. But that was the basic idea. You separate these applications that badly interfere with each other to different channels. And also prioritize latency-sensitive threads in the scheduler. So this was a combined approach. Scheduler does prioritization of the latency-sensitive, not very intensive threads, and memory partitioner, memory allocator partitions the threads separately. I don't think this will work in all cases, as Andre pointed out, but this is an interesting approach that could be combined as part of your system software. So the takeaway was intelligently combining channel partitioning and memory scheduling provides better performance than either one alone. Okay, I guess I'll give you the basic ideas and then we can finish and go for lunch. That may be another approach. One thing so far that we've looked at it was multi-programmed applications, right? We've talked about multi-program applications a lot, but multi-threaded applications also require some quality of service among different threads. So if you can identify and prioritize what threads are critical on the critical path with mechanisms very similar to what I've described in my first lecture, like bottleneck identification and scheduling. If you can identify those bottleneck critical threads, if you convey this information to the memory scheduler, you can use this information in the scheduler to prioritize those threads. And every other thread, you can try to enable them to make fair progress, such that they do not become the limiter threads. That's the idea here. That way you can improve the performance of a parallel application, multi-threaded application. And that's the takeaway. I will not get a chance to talk about this today, but I think going forward, combining this kind of mechanisms with mechanisms that help multi-programmed applications is an important direction, because in the future we'll have parallel applications running with other parallel applications, and we'll need to provide performance guarantees, or both performance, high performance and fairness to those. We've also looked at staged memory scheduling. Here, our motivation was actually looking at memory scheduling between the CPU and GPU. You have GPU and CPU sharing the memory controller. Then you have the same problem, right? You have a fairness problem and you have a performance problem. And that problem actually gets amplified if you have a GPU, because GPU turns out to be very bandwidth intensive. And it turns out the previous mechanisms that we've developed are not robust enough to handle that very large intensity, because you need very large request buffers. As a result, you need to have a very complex memory scheduler. So we tried to simplify the memory scheduler motivated by heterogeneous systems. And the idea here was to have a not monolithic memory scheduler where you search for a request every single cycle, but you divide the functional tasks of a memory scheduler into 3 portions. Each of them are kind of FIFO queues, and where each stage is significantly simpler. The first stage does robo for locality optimization, the second stage does application-aware memory scheduling, and the third stage does just DRAM timing constraints. Third stage enables DRAM timing constraints to be satisfied. And if you do the staging, this enables a more scalable scheduler. We have RTL implementations of this that show that this is much more simple. I believe the area is 66% less, and the power is 50% less than an even row hit first memory scheduler that's not application aware. And you get much simpler application-aware memory schedulers, and that can work on very large request buffers. Basically, you distribute the buffering across 3 stages. I don't know if we'll get time to talk about this, but I think going forward, again, this is an interesting area of study, because CPU and GPUs require, especially require latency and bandwidth guarantees. As a result, there needs to be more mechanisms like this going forward. Let's see, this is a very long. This is the latest work. Basically, we wanted to provide even more predictable performance. So none of these that I described here try to provide a very good guarantee on slowdowns. Everything is like best effort. This will be best effort too for real-time people here, but we wanted to try to satisfy slowdowns. That was the idea in this work, and I'll talk about this hopefully. The idea is to estimate the performance of a thread by estimating its change in memory request service rate when it's run alone versus when it's sharing resources. And it turns out this actually provides a good estimate of the slowdown of a thread. And once you have the slowdowns of a thread estimated reasonably accurately, you can enable different memory scheduling policies. You can do better stall time fair memory scheduling policies. Or you can prioritize a thread such that if a thread is beyond the slowdown bound, if a thread is slowed down more than a value x that's specified by the system software, the memory controller prioritizes that. So that's the idea over here. So I'll try to get to that. So we've also looked at prefetch-aware memory scheduling. I think incorporating other requests like prefetches and writebacks to memory scheduling is very important. I'll not talk about this, and I'll go through them very quickly. But prioritizing prefetches, depending on how they affect system performance, is important. If you have an inaccurate prefetch, you definitely want to figure that out and not prioritize it, or somewhat inaccurate prefetch. And we've also looked at designing the memory scheduler and the cache somewhat together. Because if you have a memory scheduler and it has actually row buffers open, you may want to pull in dirty lines from cache into the memory scheduler such that you take advantage of that open row buffer and improve bandwidth utilization in the memory scheduler. That was a key idea in these works. Okay. Any questions, or shall we go to lunch now? Sorry. So I'll go through some of these in a little bit more detail.
Yeah. A little bit.
Slowly. Okay, yes?
So as you put in more cores on the chip, right, so the complexity of each core usually goes down. You rather integrate more in-order cores than equal number of out-of-order cores, right? So the execution on these cores, inherently somewhat latency tolerant, it's not that high performing, right? So that in context, how do these policies come into the
So I think that's one design point. Depends on what you're running on those cores also, right? If you're running a multi-programmed application, then you may not be latency tolerant. So for example, one core is running a single-threaded application that you really care about. That may not have a lot of latency tolerance because you haven't parallelized it across cores.
What I meant to say is the 3x kind of speedups you saw with GCC running on an aggressive out-of-order
Mm-hmm.
core. It may not actually be 3x. It may be 1.5x, which you may be willing to live with without these complex policies.
I see. So I see what you're saying. Basically, if you have simpler cores, what do the slowdowns look like? So it really depends on the system. Again, if everything you have is simpler cores, your slowdowns can be still quite bad. We looked at that experiment. So this doesn't depend on the cores that much. Because what happens is the queuing delay that happens at the memory controller. Your core may have a single request that comes, and it waits for that because some other core keeps getting prioritized because of this row buffer. Right? So the slowdowns are similar qualitatively. Okay, so let's, yes?
You had a paper where you were throttling at a source. Throttling
Yes.
request was, can you explain how you decide which thread should be throttled?
So maybe,
I didn't see the...
yeah, it wasn't here because this was the smart resources approach.
Okay.
That's more of the dumb resource approach. Yes, that's the source throttling. Basically, you don't change the memory controller, but you throttle the sources. We can get to that, hopefully. Or we can do it over lunch.
It should be next day?
Next day is a different topic, but hopefully I can go over it the next day also, sure, if we don't finish it. Okay. Okay, so let's start with stall time fair memory scheduling. I'll go through this relatively quickly, but the problem is this is the behavior we observed, right? You have unfairness. One thread slows down by 5%, another thread slows down by 8x. And for most definition of fairness, this is unfair, right? And we know the problem here. So our first idea was to ensure this goal. Threads sharing the main memory should experience similar slowdowns compared to when they run alone. Different threads should experience similar slowdowns. This was what we defined as fair scheduling, and this is actually consistent with many other notions of fairness, but we're going to change that later on. This also hopefully improves overall system performance by ensuring cores make proportional progress. Basically, each of them slows down similarly. I think the projector is getting tired. Maybe even the projector is ready for lunch. We can continue with this one if you want. Maybe I'll do this. Continue with this one? Okay. That projector looked tired to begin with. Okay. Maybe I should do this so that we can see this as well. But I'd like to make sure that these recordings come out nicely before I start recording my lectures. Okay, so how do we solve the problem? Basically, the idea was to have the memory controller estimate each thread's slowdown due to interference and balance those slowdowns, schedule the request such that these slowdowns are balanced. So our definition of fairness was a DRAM system is fair if it equalizes the slowdown of equal priority threads relative to when each thread is run alone on the same system. So I'm going to define several metrics. DRAM, because the memory controller is aware of the stall time because of DRAM, right? DRAM-related stall time is the time a thread spends waiting for DRAM memory. So we have two values. One is stall time shared, which is the DRAM-related stall time when the thread runs with other threads. And stall time alone is the DRAM-related stall time when the thread runs alone on the same system. So the memory slowdown is simply stall time shared divided by stall time alone. This is the relative increase in stall time. And the stall time fair memory scheduler, STFM, aims to equalize the memory slowdown of interfering threads without sacrificing performance. That's the goal. That doesn't always happen, right? Sometimes you actually sacrifice performance. So we thought this was a good metric because this actually considers inherent DRAM performance of each thread. If you actually try to equalize stall times, that's not a good idea because it doesn't consider the inherent performance of each thread. And this hopefully allows proportional progress of different threads. So the scheduling algorithm, if you have these values, for each thread, the DRAM controller keeps track of stall time shared. This actually can be done at the core and communicate to the controller. And this is easy when you're running together with other threads. You figure out when you're stalled for memory. And estimate stall time alone. And this is actually it's a very difficult part if you're actually trying to do it within the memory controller. I will not talk about this, but hopefully when we get to our recent work, we have a mechanism to approximate it without actually trying to do it. So I'll give you the basic idea of what we try to do over here. And this is actually true for what we tried to do in the source throttling work also. Basically, the idea was if the memory controller picks thread A over thread B, it increases some number of cycles saying that I've delayed thread B for this number of cycles. And this thread B has incurred some stall time. That's the approximation. You could do it for row buffer hits and misses. If the memory controller keeps track of shadow row buffers for different threads, and when it schedules a request from a thread, it checks if it would have been a row hit or row miss if the thread were running alone. And you can actually figure out the difference in excess cycles, how many more cycles you've spent because you're sharing resources with other threads. So this turns out to be very difficult to estimate very accurately, right? If you think about it, what we were trying to do was to emulate behavior of a system when it's running alone, only this application. And that becomes very complicated if you want to do it very perfectly. So we approximated things. But it worked reasonably over here. So once you have these two values for each thread, the memory controller computes slowdown, which is stall time shared divided by stall time alone for threads with legal requests in a cycle. And it computes unfairness, maximum slowdown divided by minimum slowdown in the system. That was the definition of unfairness. And if unfairness is less than some alpha value, which is the maximum tolerable threshold of unfairness, the DRAM controller behaves as usual. Row hit first requests are prioritized. It's not thread aware. If unfairness is not tolerable, then the memory controller uses a fairness-oriented scheduling policy, switches to this policy, where it prioritizes requests from the thread that has been slowed down the most. And the other priorities are still similar under that. So basically, the memory controller operates by computing slowdowns, estimating unfairness. If unfairness is tolerable, it uses a throughput-oriented scheduling policy. Otherwise, it switches to the fairness-oriented scheduling policy. And pictorially, if you look at the two applications that we've looked at, this is stream. The red one is random. And the memory controller keeps track of the slowdowns. And unfairness is basically the division of these slowdowns. And you have alpha value, which is the maximum tolerable unfairness, which can be set by the system software. And the memory controller, let's say, keeps scheduling requests initially in the throughput mode. And once it prioritizes thread 0's request over thread 1's request, thread 1 gets slowed down and the memory controller keeps track of that and unfairness increases. After a while, thread 1's slowdown increases and it becomes unbearable. It becomes greater than the alpha value. As a result, the memory controller switches to the throughput or fairness-oriented scheduling policy. It prioritizes the thread that has been slowed down the most, T1 in this case. And as a result, now T0 slows down because compared to when it's running alone, it should have serviced its request, and that reduces unfairness in the system. And the memory controller switches back to the throughput-oriented scheduling policy. And later, thread 1 slows down more again, and the memory controller switches to the fairness-oriented scheduling policy. So it tries to keep this unfairness in check by switching between these two policies. And that's the idea. Right?
And you can do that kind of thing at a very low granularity level?
Cycle by cycle, you mean?
Yeah, or request by request.
Yes, you can do it. It's complex.
It's complex.
That's right. So we'll try to fix this complexity problem later on. But this was our first idea. It was, it was an interesting conceptual. I would call this conceptually interesting, but implementation-wise, it's complex. And the upsides, I think it identifies fairness as an issue in multi-core memory scheduling, which is interesting. It's good at providing fairness, and being fair also improves performance because it allows cores to be utilized better. The downsides, I think one downside is it doesn't handle all types of interference. It's actually somewhat complex to implement. You can simplify a lot of these things. You can actually simplify that division. You don't need to do a division, for example. But you still need to keep track of some interference, which is the shadow row buffers and the interference, and that actually adds complexity, I think. You don't have to be perfect in this. And slowdown estimations actually can be incorrect. So I'll show you results later saying that on average, the slowdown estimations are incorrect by 30% or so. So we'll try to develop a mechanism that's much better in estimating the slowdowns. Okay. So I think this is complex to implement. So we wanted to design much more simpler mechanisms. But we also observed other things. And let me tell you about that other problem due to interference. Today's processors try to tolerate the latency of memory requests by generating multiple outstanding requests, out-of-order execution, non-blocking caches, run-ahead. They all try to parallelize memory requests. And this is effective only if the DRAM controller actually services the requests in parallel in DRAM banks. In a single-core system, this is mostly true. But in a multi-core system, multiple threads share the DRAM controller. And if the DRAM controller is not aware of a thread's parallel requests, it can service each thread's outstanding request serially and not in parallel. Let me give you this pictorially. I think I've already given you the basic ideas here. But let's say you have a single thread, thread A. It generates 2 requests, and it needs to wait for those 2 requests. And these go to the memory controller with 2 banks. Let's assume that they go to 2 different banks. And the memory controller starts servicing the first request, and then it starts servicing the second request. And these 2 requests are serviced in parallel. As a result, the thread stalls for 1 bank access latency approximately for 2 requests because the requests are serviced in parallel. Let's take a look at what happens if you have 2 of these threads running together at the same time. A and B, very similar threads. They both generate 2 DRAM requests at similar times, and these go to the memory controller in this order. Let's say the memory controller is not aware of these threads' parallelism, and it schedules the requests in the order they arrive. It takes thread A's request to bank 0, schedules it, and then thread B's request to bank 1, schedules it. And while these requests are in progress, both threads stall. Then later, thread A's request completes. The memory controller takes thread B's request to bank 0 and schedules it. And after a while, bank 1 becomes free, and the memory controller takes thread A's request to bank 1 and schedules it. And while these 2 requests are being serviced, both threads stall again. And after a while, both requests complete. If you look at this, what happened was each bank access latencies of each thread was serialized, right? So you get approximately 2 bank access latencies per thread. So can we do better? That was the question we asked. And you can actually do better by actually doing what I've described to you. The memory controller somehow realizes that after it schedules thread A's request to bank 0, thread A has another request to bank 1. And if it services that, thread A's request can be serviced in parallel. And once the memory controller realizes that, these 2 requests will be serviced in parallel. Both threads stall because their requests are not done. After a while, banks become not busy, and memory controller takes thread B's requests and schedules them to different banks. During this time, thread B stalls, but now thread A can continue computation because all of its requests are serviced. As a result, what we have here is saved cycles compared to the previous schedule. And this improves system performance because it reduces the average stall time of threads from 2 bank access latencies on average to 1.5 bank access latencies in this case. And this actually becomes a bigger problem as you keep adding more threads, even if you had more banks, because you can imagine 4 threads, 4 banks, and they all get serialized in different banks. Whereas if you perfectly obeyed their parallelism, you could get much better system performance. So I've already given you the ideas to fix this problem, right? How do you actually design a scheduler like this? That was the next step that we want to do. Basically, first you want to be parallelism aware. You want to schedule requests from a thread to different banks back to back. But as I told you, this can cause starvation. So you would like to also batch the requests. And that's the idea. So I've already shown you this, so I'm going to skip this quickly. But I'll describe how you can actually implement this, if that's interesting. OK. OK. So that's the basic idea. Then the key question is, how do you actually achieve both of these at the same time? So PAR-BS, parallelism aware batch scheduling, has 2 components. One is request batching, and the other is within batch scheduling. Request batching is actually a substrate that can enable many different unfair scheduling policies within itself, because this enables starvation freedom and some kind of fairness. But we're going to make it parallelism aware within the batch. Let's take a look at request batching. This is actually relatively simple to implement. Each memory request has a bit that says marked bit associated with it. And memory controller, when there are no requests that are marked in its queue, it goes into its queue and marks up to a number of oldest requests per bank for each thread. And we call this the marking cap. These marked requests, after that point, constitute the batch. And the memory controller forms a new batch when there are no marked requests left. This is a single batch, oldest batch. And marked requests are always prioritized over unmarked ones. This ensures that there's no reordering across the batches so that there's no starvation. And reasonable fairness. Then the key question is, how do you prioritize requests within a batch? So within a batch, you can actually use any existing or future DRAM scheduling policy, right? You can use draw hit first and then oldest first. This exploits robo for locality, but we would like to also preserve intra-thread bank parallelism. So to do this, we would like to service each thread's request back to back. So how do you do that? So we have the scheduler compute a ranking of threads when the batch is formed. And higher ranked threads are prioritized over lower ranked ones. Doing this, and all bank schedulers actually obey this ranking. This improves the likelihood of requests from a thread to be serviced in parallel by different banks. So a thread can be prioritized because all threads are prioritized in the same order across all banks. So then the key question is, how do you actually compute this ranking? What's a good ranking policy? You can randomly rank threads, right? And we explore that in the paper. You can do round-robin order. But the ranking scheme actually affects system throughput and fairness. We'd like to ideally maximize system throughput and minimize unfairness, which is equalize the slowdown of threads. It turns out, so what do I mean by maximize system throughput? We'd like to minimize the average stall time of threads within a batch. And the hope is that that maximizes system throughput. If you would like to minimize unfairness, ideally we would like to service threads with inherently low stall time early in the batch. And the insight here is very similar to what we've discussed earlier. If you have a memory intensive, consider 2 threads. One is very memory intensive, one is not memory intensive at all. If you delay both threads by the same amount, the impact on the memory intensive thread is not as much. Whereas the impact on the memory non-intensive one, the compute intensive one, is a lot, because it makes very fast progress. You delay it by the same amount, it slows down significantly. So it turns out the ranking policy that achieves both of them is similar. Basically, if you do shortest job first or shortest stall time first ranking, you could get both of them. Not perfectly, but at least within some reason. So if you do, that's the idea. We're going to try to do shortest stall time first ranking. We're going to estimate the stall time of threads somehow, simply, and rank them based on that stall time. And if you do this, actually, this shortest job first is a very old result, right? If you have a single server queue, this provides optimal system throughput. The idea here we're going to do, but this is not going to be optimal. What I'm going to do is not optimal at all. But the controller will estimate each thread's stall time within the batch, and it will rank threads with shortest stall time higher. Let's take a look at how this actually works. How do you actually do shortest stall time first ranking? We're going to approximate it because actually doing this is very complex too. We're going to define two values in the memory controller for each thread. One is the maximum number of mark requests to any bank, which is the max bank load. And the threads with lower max bank load will be ranked higher. And we're going to have total number of mark requests for each thread. This is the total load of the thread. Let's take a look at this pictorially because it's a lot easier to understand with an example. Let's say we have these 4 threads, 4 banks. Let's compute these two values for these different threads. So if you look at thread 0, its max bank load is 1 because the maximum number of requests it has to any bank is 1. Its total load is 3. It has 3 requests. If you look at thread 1, its max bank load is 2 because it has 2 requests to bank 0. And its total load is 4. If you look at thread 2, its max bank load is 2 to bank 1 and bank 2. And its total load is 6. And if you look at thread 3, this has the highest stall time estimated. It has 1, 2, 3, 4, 5 max bank load, and its total load is 9. So based on this ranking policy, thread 0 should be ranked higher than thread 1, higher than thread 2, higher than thread 3. And the tiebreaker between thread 1 and thread 2 is the total load. And this is an estimate, of course. So let's take a look at what happens if you do this ranking, if you implement this ranking in the memory controller. This is the baseline scheduling order, let's assume. This is the arrival order. And this is also, let's say, the baseline scheduling order. I'm assuming row buffer conflicts here, but the paper actually has an example with the row buffer hits. You get similar behavior. And I'm going to assume that requests are serviced in this order with some time units. So the first set of requests are serviced after 1 time unit. And I'm ignoring the bus again, serialization due to bus. But if you add them up again, you'll get similar results, except with more complex observations. And at time unit 2, all of these requests are serviced. So if you calculate each thread's stall time based on this, thread 0's last request is serviced after time 4. Thread 1's last request is serviced after time 4 again. Thread 2's last request is serviced after time 5. And thread 3's last request is serviced after time 7. If you average these stall times, you get average of 5 bank access latencies. Now let's take a look at what happens with the scheduling order that I've discussed. If the memory controller determined that scheduling order, it ranks thread 0 first, thread 1 next, thread 2 next, thread 3 next, last. So basically, thread 0's requests are prioritized within this batch, which means that thread 0's requests are serviced first. As a result, its parallelism is preserved, and its last request is serviced after 1 bank access latency. Thread 1's requests are prioritized second. As a result, thread 1's requests are prioritized next. Its last request is serviced after time 2.
That suppose that you are able to serve threads for different, the request for different threads at the same time.
That's right, yes. So the assumption is that each bank has a scheduler, separate scheduler that picks with the same ranking.
Okay.
Yes. And that's the state of the art today. Well, not the thread-aware one, but state of the art is each bank is a scheduler of its own. And then they arbitrate for the buses. Thread 2.
You have to have a global ranking.
Yes, ranking is global across banks.
And this information is somewhere distributed.
If you have multiple memory controllers.
Yeah.
Yes, that's right. And that's the problem that we try to solve in the next work.
Okay.
Yes. So for this work, that's a very good observation. First of all, within a memory controller, you have to have a ranking that's global across the banks. And if you have multiple memory controllers, and if you spread threads requests to different memory controllers, you have to have a global ranking. And the solution that we have, which doesn't work with this scheduler, is all memory controllers coordinate somehow. Basically, they send how many requests they have for each thread to a meta controller, and that meta controller computes the ranking and distributes it back. It doesn't work for this controller because this controller at a very fine grain forms the batches. By the time you distribute to everyone, the batch is almost gone. But if you have a much coarser grain scheduling interval, ranking interval, this works. So that's the next work that fixes that problem. Okay. But that's a very good observation too. So thread 2's requests are prioritized next, so thread 2's requests are serviced this way. Its last request is serviced after 4 time intervals, and thread 3's requests are deprioritized. Its last request is serviced after 7 time intervals. So in this nice example, you get 3.5 bank access latencies, which is 30% less average stall time over here. It doesn't always work this nicely, of course, because sometimes thread 3 gets delayed much more, but this works nicely for illustration purposes. Okay. Okay, so how do you, let's put it all together. What's the scheduling policy in the end? Basically, the scheduling policy incorporates both batching and ranking. Batching means marked requests are prioritized over every other request, so that bit determines the highest priority. Within batch, row hit requests are prioritized over others, and the third priority level is higher ranked threads are prioritized over others. And you could ask, why not do this one first and row hit request next? We tried that also, and these are very similar. So there's no easy way to fix this problem, I think. There's an inherent divergence between locality and parallelism, and we're trying to get both locality and parallelism here. And the paper has a lot of details on these scheduling policies. And lastly, older requests are prioritized over others. So the 3 properties, we try to exploit both robo for locality and intra-thread bank parallelism. This is work conserving, meaning that this is a priority order. If a bank has requests that are not marked, that bank services the unmarked request. It makes no sense to delay that request. Marking cap is an important parameter. This is, remember, how many requests a thread can inject into a batch. And if this is too large, your batches are very large. As a result, what happens is, if a request comes in from a memory not-intensive thread, it may end up being out of the batch. As a result, it has to wait for this long batch to complete. So that's not good for performance. If the marking cap is too small, then you finish those requests, so you do not exploit robo for locality very well within a thread that has good robo for locality, because you have to finish those requests from all threads first. So this is not, there's no perfect way of determining it. We determine it empirically, and we have good results. And there are many more trade-offs in the paper, too. So what's the hardware cost of all this? This is actually much more simple to implement than stall time fair memory scheduling. The storage cost is low. There are no complex operations, and you can approximate whatever is needed, and it's not on the critical path also. And you don't need to try to emulate what's going on with the memory controller. So let me give you a little bit results. This is results average across many applications on 4-core, 8-core, and 16-core systems. And this is the unfairness. So lower is better. And unfairness is defined as maximum memory slowdown in the system divided by minimum memory slowdown in the system. FRF-CFS is an existing scheduler. That's the row hit first scheduler. So it's very unfair according to these results. And its unfairness increases as you increase the number of cores, although these are for different workloads. So this FCFS is no scheduling at all, first come, first serve. NFQ is network fair queuing. Basically, you apply the fair queuing principles to the memory scheduler. But this doesn't take into account the specific aspects of the memory scheduler, like bank parallelism and locality. And stall time fair memory scheduling is what I described, and PAR-BS is what I just described. So overall, PAR-BS improves on fairness compared to stall time fair memory scheduling significantly. And stall time fair memory scheduling improves on fairness compared to the best previous scheduler, which actually depends on the number of cores. In terms of system performance, this harmonic mean speed up normalized to first ready, first come, first serve. Again, stall time fair memory scheduling provides higher performance than previous schedulers. And if you look at previous schedulers, sometimes doing no scheduling is better than first ready, first come, first serve, row hit first scheduling. If you have applications that are intensive in terms of robo for locality. But sometimes row hit first scheduling is better. This is a very average result, by the way. It's all average across many applications. Overall, stall time fair memory scheduling improves performance because it improves fairness, and parallelism over batch scheduling improves performance a little bit more over stall time fair memory scheduling. And the reason is there are two reasons. One reason is it improves fairness because it provides proportional progress, and the second reason is it services the thread's request in parallel. So it preserves intra-thread bank parallelism. Okay. So what are the upsides of PAR-BS? As with everything, there are upsides and downsides. Upsides is it basically identifies the problem of bank parallelism destruction, which is, I think, interesting across multiple threads, and tries to solve that problem. And it is a simple mechanism. You could argue nothing is simple, but it's a simpler mechanism than stall-time-fair memory scheduling, although what I will go over will be much simpler than this. The downsides, as I described earlier, it doesn't always prioritize latency-sensitive applications. So if you have an application that generates one request, it needs to wait for the next batch. And as a result, these compute-intensive applications get delayed unnecessarily. So this leads to lower overall throughput. And as Andre pointed out, implementation in multiple memory controllers needs coordination for best performance. It needs coordination because you want to determine a single global ranking. Actually, we did the experiment. What happens if you have just local rankings without coordinating? What happens? You get still good performance as long as your requests are nicely distributed across memory controllers. As long as you have similar request distribution, you get good performance. The problem is, if that doesn't happen, you need too frequent coordination because batching occurs at a very fine grain. According to our results, the batches were on the length of 2,000 to 5,000 cycles. And you don't want to coordinate every 2,000 or 1,000 cycles. So we tried to solve both of these problems in the next work. And I'll briefly describe the idea. And I don't think we have a whole lot of time to finish all of these ideas. So this is the last one?
Yeah, you got it's a quarter past noon.
Okay, sure. Any questions before I jump to this? Okay. Let me briefly describe the idea here. Basically, we wanted to solve both of these problems, but we also wanted to rethink memory scheduling at that time. And I think this is still not the best one. The thread cluster memory scheduling is a better one, but I'll give you this one, and you can continue with the other one. So if you think about memory scheduling, memory accesses, a thread actually alternates between two states. We'll call these episodes. You have the compute episode where the thread is not memory bound. It doesn't have any memory requests outstanding. You have the memory episode where the thread is waiting for a memory request, right? At least one memory request. And memory episode is low performance, low IPC for that thread, instructions per cycle. Compute episode is high IPC. From the memory scheduler's point of view, the goal is to minimize the time spent in memory episodes because the memory scheduler is exposed to those memory episodes. And we're going to try to design a memory scheduler that tries to minimize the time spent in memory episodes to maximize system performance. Now, in hindsight, I think a better way of designing the system is to maximize the time spent in compute episodes. So if you can actually do the other way around, if you can try to predict how long your compute episodes are and try to maximize them, perhaps you can achieve a much better system. Maybe that can be something else that people look at. But if you want to minimize memory episode time, you like to prioritize the thread whose memory episode will actually end the soonest. This actually minimizes the memory time spent in memory episodes across all threads. This is actually supported by queuing theory. In a single server queue, shortest remaining processing time is optimal in providing maximizing throughput, job throughput. Now, we're not a single server queue. If you look at a memory scheduler, it actually has lots of banks, and it's not single server. It has this row buffer, which actually reduces that single server queue property even more, right? There's locality incorporated in it. So it's not going to be optimal, but we're going to use the same principle. So if you would like to do this, what we would like to really do is to predict when a thread's memory episode will end. But we do not know that, right? If a thread has started its memory episode, the memory controller knows it starts generating requests at this point, but you do not know how long the thread will keep generating requests, how much the episode will last. So the observation in this work is you could actually predict this. Past is a good predictor for future. Basically, the memory controller can keep track of how long the episode has lasted and can use that as an estimate for how long the episode will last. So the memory controller, in other words, can keep track of the attained service of a memory episode of a thread or of a thread and use that as a predictor for the remaining service. Why? Well, why is actually empirical. Memory episode lengths are Pareto distributed, and maybe there's an underlying reason in the programs, but let me give you the distribution, and people have observed similar behavior in other parts of the systems as well. So if you look at this, this is one example, and there are many examples from spec workloads. X shows the number of cycles a memory episode has lasted, and the Y shows the probability of that memory episode being greater than that number of cycles. And if you plot this on a log-log scale like this, you have a linear fit curve. That means that this is a Pareto distribution. So it's a heavy tail distribution. This means that the longer, with a decreasing hazard rate, this means that the longer an episode has actually lasted, the longer it will last further. So people have observed this in things like job distributions in operating systems, or file size distributions in network file transfers, for example. It turns out the file sizes are Pareto distributions. If you transfer the file for a long time, it's very likely that you're going to transfer that file much longer. Whereas if you transfer the file for a short time, it's likely that that transfer will die soon. It kind of makes intuitive sense, right? That you're going to die early. My favorite non-technical example, if you have slept for a long time, it's likely that you're going to sleep for longer. Whereas if you slept much shorter, it's likely that you're not going to sleep. Now that's that's not supported by any kind of empirical data, but this is that's the empirical data. People have observed this interestingly, and they try to optimize FTP operations, FTP transfers. They've tried to optimize job scheduling policies in the operating system because they've seen that this is actually true for job distributions in Linux in 1990s. And they've actually developed a lot of these scheduling policies.
But in
Yes.
a memory episode, as you described it, cannot last longer than it will last only if it is sustained, because you need some data
That's right.
to go back.
That's right. So.
Because of your reorder buffer and so on.
Mhm.
So if you just say, oh, my memory episode will be long, so I do not serve it, then it remains very long just because you
That's right.
serve it.
That's right. But then you're not serving it because there's some other thread that hopefully doesn't have a long memory episode, which means that it's probably compute intensive, right?
Yeah, maybe.
So I think the reason some threads have longer memory episodes is, I think of this at a thread level. Some threads inherently probably have longer episodes because they generate lots of requests. As a result, their memory episodes are long, right? Even if you have a long reorder buffer, then you miss, and that gets serviced, but then you have another miss that keeps memory busy.
But if you are avoiding to miss to serve it, it just stops.
It just gets delayed, that's right. It doesn't get stopped, I think, but it just gets delayed. So that's the downside of the approach. I think you're pointing to the downside, which is if you have a very intensive thread, that gets delayed a lot. Yes, and that's going to be the downside. It's not going to be a fair scheduling policy.
Okay.
That's going to try to maximize performance. So, okay, basically we've observed this, which means that the longer an episode has lasted, the longer it will last further, which means that attained service of a thread actually correlates with the remaining service. And we're going to use this observation to devise a scheduling policy. We're going to favor the least attained service memory episode, which means that favoring memory episode which will end the soonest. As a result, that will hopefully minimize the time spent in memory episodes. So let me recap a little bit. The idea is least attained service memory scheduling. We want to prioritize the memory episode with the least remaining service. Why? Because queuing theory says that prioritize the job with shortest remaining processing time. This is probably optimal with some other system. A remaining service, we found that remaining service correlates with attained service based on empirical data. And attained service can be kept track of by a per thread counter, one counter per thread. That counter is reset when the memory episode starts, and basically it gets incremented while the memory episode is going on.
You are defining the bounds of the memory episode by saying there's no request anymore for that thread.
That's right.
So
You got rid of the counter. You reset the counter. Exactly. But we're going to make it more coarse-grained because this doesn't take into account something because of what I suggested earlier. But let's assume that this is you reset that counter at the beginning of the episode. And that's all you need on a per thread basis if you want to do it this way. Now you can prioritize the memory episode with the least attained service. And hopefully you can minimize the memory episode time spent in the entire system. The downside of this approach is it doesn't consider long-term thread behavior. So if you look at thread 1, and thread 2. Thread 1, if you look at just the memory episode of each thread, this one is a short memory episode, and this one is a long memory episode. And what we've done would prioritize this thread over the other one. But if you look at the long-term behavior, the thread may go back to a short memory episode after an even shorter compute episode, right? This is the yellow one is a compute episode. It computes very little and then goes back to a memory episode. Whereas if you look at thread 2's long-term behavior, it would go to a compute episode that's very, very long. So ideally, you would probably like to prioritize this thread because this will keep its core much busier, whereas this one will not keep its core busy. So prioritizing thread 2 would be more beneficial because it would result in long stretches of compute episodes. And going back to what I said earlier, we were looking at it from the memory controller point of view, minimizing memory episodes. If you're actually trying to maximize compute episodes, you would be doing exactly this, right? You won't be starting out, you won't be having this anomaly, I think. Okay, so how do you actually fix this problem? The way we fixed the problem was basically look at a coarse grain interval in terms of memory episodes. In terms of looking at each memory episode, we divide time into quantums and keep track of long-term thread behavior. Basically, millions of cycles, we keep track of the attained service of that thread during those millions of cycles, how long it has stayed in its memory episode. So how do we rank the threads once we have this? Basically, during a quantum, each thread's attained service is tracked by the memory controllers. Let's assume that this is attained service I during that quantum. At the end of a quantum, each thread's total attained service is computed with this equation. Basically, attained service in the previous quantum weighted by this weighting factor plus attained service so far, total. And this gives another level of history here because you have more bias towards history if your alpha is higher. And the reason is threads have very long-term behavior. You don't want to relearn this behavior episode by episode, right? That's the main problem. That's the main thing we're trying to do. Threads are ranked, favoring threads with lower total attained service in this case. And attained service is now quantum-based. In the next quantum, threads are serviced according to their ranking, favoring threads that have lower total attained service. So that's the idea here. And you can now coordinate better because the hope is that this quantum is long enough. At the beginning of the quantum, all memory controllers send their information to a centralized memory controller, and that centralized memory controller computes this ranking and distributes it back to the memory controller. And this quantum is 10 million cycles in the paper. So the scheduling algorithm after this is simple. We call it adapter per thread least attained service scheduling algorithm. The prioritization order is this way. The first is if a request has been outstanding for a long time, we schedule it. This is to prevent starvation. Because there's no other starvation freedom guarantee with least attained service. Actually, least attained service is not bad because over time, if you not service a thread, it accumulates a counter. But that may be a very long time. So to maximize performance, least attained service rank thread is prioritized over others based on the ranking. And the third prioritization order is row hit requests are prioritized over others and oldest request over others. And I already told you this one. How do you coordinate memory controllers to agree upon a consistent ranking? So what is the performance? And, well, we will not look at fairness maybe, but what is the performance of this? This is, I'm showing you a number of memory controllers on the x-axis and system throughput on the y-axis, and 5 different controllers. No scheduling, first come, first serve, row hit first scheduling, stall time fair memory scheduling, parallelism over batch scheduling, and atlas. And if you look at the 4 memory controller case with 24 core system, you get about 8.4% performance improvement compared to parallelism over batch scheduling. And if you, overall the observation is that it consistently provides better performance than previous scheduling algorithms. Its performance actually increases as memory bandwidth becomes more scarce. So if you look at this with 24 cores and 16 controllers, which is a very expensive system probably, scheduling doesn't matter that much, right? Because you have a lot of bandwidth. If you look at this as a very starved system, 24 cores with 1 controller, the performance improvement is 17%, which is higher than the performance improvement that you get as you increase the memory controllers. So this turns out to be at least more efficient than other scheduling algorithms in maximizing system performance because I believe it prioritizes these compute-intensive threads that make better use of that little bandwidth that you give them. What about system? This is system throughput as you increase the number of cores from 4 to 32. And comparison point is the best previous scheduler, parallelism over batch scheduling. As you increase the number of cores, again, performance improvements, relative performance improvement compared to the best scheduling algorithm increases. And with 4 cores, it's not that big of a difference, but with 32 cores, the performance improvement is 11% compared to PAR-BS. And again, the reason probably is because these threads that are attaining less service are making better use of the little bandwidth that you give them in terms of better translation of that to overall throughput or overall progress. Let's take a look at the properties of this. We actually had 3 goals. We wanted to maximize system performance, and least attained service ranking actually achieves that. Atlas still preserves bank-level parallelism because we keep the thread ranking, and it tries to do best with robo for locality. This is more scalable to a large number of controllers because there's very infrequent coordination, whereas coordination was high with PAR-BS. It's also configurable by system software. We actually scale the attain service with thread weight. The system software can convey thread weights, and the hardware can scale the attain service with that weight. For example, if a thread is very important, you can give it very large weight in the system software, and if the hardware divides the attain service with that weight, you'll get attain service close to 0. As a result, that thread is prioritized. And I do not remember the exact hardware cost, but attain service requires a single counter per thread in each memory controller, and you need all of these other counters to ensure history is incorporated. But that's a relatively simple controller compared to the other ones. So this has downsides also. Upsides, it is good at improving overall throughput. Compute-intensive threads are prioritized. It's low complexity. And coordination among controllers happens infrequently. Downsides, it's not fair. Lowest or medium-ranked threads get delayed significantly. Because if you think about it, you have these mice, little threads, and you have these elephant threads, and you have things in the middle. These elephant threads, if there are lots of mice, these elephant threads get delayed for a long time. Right? So it leads to high unfairness. And that's what we try to solve in the next work, but we can stop. It's 12:29, yes.
What is currently implemented controllers
So today I do not know.
If you redo the experiment of that you were illustrating in 2007, will you get the same thing or?
So that I think I know. My feeling is no, because people have tried to fix the problem. But I don't think they've done something like thread cluster memory scheduling, for example, yet.
Probably they have not taken your approach, but another one or a similar one. But they have taken into account the problem.
Maybe not all companies, but I believe they have taken into account some of the problems. But I don't think, I think you can still write programs. So I'm not sure about this, but because I haven't done it. But my feeling is you could try to write a denial of service program, but that'll be a little bit harder than yesterday.
Okay.
So I think, for example, they've tried to reduce the downsides with first ready, first come, first serve by reducing the amount of reordering that happens. Like you can have a cap as to how many requests can be reordered over the oldest request.
Which is a little bit like your batch.
That's right. So they may have, I know people have looked at batching. I don't know what they've implemented. And I haven't tried to demystify today's schedulers yet.
Yeah, it's not easy.
It's not easy, I know.
Yes.
I know. Today, even the address mappings are not easy, right? You do not know what address is mapped to what bank or what controller.
Few questions?
So if you were the compiler guy using normal hardware, what would you do?
Oh, so I think.
Or the operating system also.
Sure. For the compiler guys, what I've described so far, I think this you should not really need to worry about because Actually, you may do a compiler optimization if you're a compiler guy. It may not matter at all because somebody is denying service to your program, right?
So can I take this into account? Try to make sure that I know what's going on?
So as a compiler person, I think it's very, very difficult, right? Because the compiler has no knowledge of what other application is running with the application that you're trying to compile, I think. JIT compiler. Huh. So I think the best I can think of as a compiler guy is to make sure that your thread denies service to others. if your system is unfair, the best thing you can do is make sure that it's a very memory-intensive thread. The problem is now you're reducing the performance of your application probably because of that, right? Well, actually, with a streaming thread, if you convert your thread, if you can do this, from random access to streaming, you would likely deny service to others if you preserve the same memory intensity. That improves your performance too, probably. But I think as a compiler guy, it's very hard to find recommendations to fix this problem. As a system software, then I have lots of recommendations if you would like to fix this problem in the system software. But I think this should be a given. A system being in a predictable way, not fair way, should be a given to people who optimize programs such that they don't go crazy when their program runs with one application versus another application.
Can you get data from the memory controller? What's going on, steady states?
So it's
Performance counters?
sure. So we've looked at that a lot. It's very tough. You could get the memory intensity of a thread, but there's, as far as I know, there's no memory controller that exposes the interference counters, for example. How much interference are you experiencing? Even that's not exposed as far as I know. Even how much row buffer locality you have on a per thread basis, per application basis is not exposed, as far as I know today. Overall, row buffer locality is exposed in some controllers, but that doesn't give you much if you have multiple applications.
Okay, so now.
Okay.
So, thanks.
Okay, thanks.